I apologize if this video is less clear than what I intended to be, simply because it is my first time using this one. Alrighty, so let's get this party started. So just as a quick recall, we are working with probability, and specifically probability distributions or probability models in Chapter 7. We're going to be looking at a continuous model, which means when I think about the possible values for my random variables, random variable in this case, there is an infinite number of options. So you should be thinking the range is endless for what could happen. And that's very important with how this looks and how it feels. As it turns out, the one thing we need to be able to do this and go forward is actually z-scores. We learned about z-scores back in chapter 3, and if you remember, the formula for a z-score was, z equals x minus the mean, I'm going to use mu for the mean here, divided by the standard deviation. And we always thought of the z-score as the number of standard deviations, a value like x, was away from the mean. So it was a way of measuring how unusual you were because it was telling us how far from average you were. And remember, the larger it was, the further it was from zero. And the way you were kind of measuring that was the standard deviation, which is average distance from the mean. So this is like our unit of how far we are on the ruler, and then the z's are like the ticks on the ruler for how far you are away. So what we're going to look at today is what's called the standard normal distribution. So this is going to be, done drawing, what we look at today. Woohoo! So the standard normal always has the same three characteristics. So it is unimodal, bell-shaped, and symmetric. So for some reason on this version of my notes I don't have the picture of it, but you do. So I'm going to draw it. That should go real well, right? So when we picture the standard normal distribution, you should have a nice clean bell curve. Woohoo! Now, since it's symmetric and bell-shaped and unimodal, you know that it has that one peak in the middle, which means you should think, oh, well, then the center is going to be dead center thanks to symmetry. So this is where the mean is. Yep. And then in looking at the mean, it turns out that the standard normal the normal distribution has some very specific characteristics. So I'm going to draw 3 lines roughly in here using the pencil. And as I draw these on the shape, I know where these go because we're going to talk about a rule for this later that tells us roughly where each of the values fall for the z-scores. So for a normal distribution, this distance right here is roughly 1 standard deviation. So adding 1 standard deviation to the mean, I end up about here. Woohoo! And then here is adding 2. And then here is adding 3. So a long, long time ago, I told you that, well, not a long, long time ago, like a couple chapters ago, being 1 standard deviation away from the mean isn't very unusual, and it isn't, because if you look at 1 standard deviation away in either direction, so not only mu plus sigma, but mu minus sigma, so from here to here, that's a big lump of change. That's pretty much everything, so there's nothing unusual about that. But if you're more than 2 standard deviations away from the mean, that's pretty unusual. So that's falling out to like this range, which is pretty much everything. So you notice these tails are really narrow. So if you're more than 2 away, you're like in these narrow, small spaces that are much farther from the center, especially if you were more than 3 away. Woohoo! 3 sigmas. Okay. As it turns out, once you know the mean, and what you've seen me draw in here at the spread, you know what all normal distributions look like. So this one in particular I've drawn, and I'm going to write the symbols for this for you, this is x. Ooh, I didn't give it a name, so you're supposed to put it on the x-axis, which I didn't label. That would be my x. And the way we write these, because they are so common, hence the name, it's normally what you get, is distributed normally, that's supposed to be a capital N, with mean, mu, and standard deviation, sigma. So we have like a shorthand symbology for what this looks like. Hey, my variable x, this just means is approximately, is distributed, not is approximately, it is this, is n for normal, and then it describes the mean and standard deviation, because once you know those two for the normal, you know exactly what it looks like. Woohoo! So the standard normal distribution is the one we're going to use a lot to do a bunch of things. And a couple things about this. First of all, the symbol we use for this is z because it's the standard normal distribution. Sorry, it's the standard distribution of z-scores. So exact same idea, but I'm going to be doing z-scores. It has mean 0 and standard deviation 1. And it turns out that this is pretty special. So let's draw what this one would look like. Are you ready? So here, I'm going to try to draw this. Woohoo! I don't know why this one's taller, but it is. There we go. Let's change our colors here. Let's do blue. That'll be fun. So this one, the mean is 0, so right smack dab here in the middle, I'm going to have a 0. And then it has standard deviation 1, so going up one standard deviation is just going up 1, so this is a 1. And then one more would be 2, and then one more would be 3. This is why I was telling you when z is bigger than 3, you're very unusual. And then this would be -1, -2, and -3. Yay! So this would be z. That's it. Done. So then what's the normal probability model? Well, that's when you want to find when you want to find probability on the normal distribution, and in order to do that, you are going to be using area. So area is making probability for these distributions. Woohoo! And the way we do this is actually how you traditionally do area in mathematics, and that's actually using calculus. So since we don't do calculus and statistics and we tend to rely on technology, we're going to use two different ways to do this. So the first way I'm going to show you is how to do it by hand, which is essentially the manual version, and then as always I'll show you the technology version using Minitab, well, the next day. So we're going to use two methods. So we're going to find this two ways. We're going to use something that's called a z-table, or we'll use Minitab. But the important thing to keep in mind is that formula for a z-score. Z equals x minus the mean divided by the standard deviation, because that is what's going to help us do this easier. Let's see how we do. So I have the table ready, and I'm going to pop it up here in a second. So the first thing I'm going to do for all these is I'm actually going to draw them, because I feel like the picture helps you picture what's happening. So as I go through these, think a little bit about what you think is happening here. So I'm going to do standard normal, which means mean 0, standard deviation 1. Here's my little ghosty guy that's supposed to be perfect. I always mark the mean on these because I think it's easier to position yourself if you know what the center is. In this case, I know the center is 0. And here in particular, I want z's less than or equal to 0, so everything less than the mean. So I'm going to shade that in with some highlighting here. Ooh, that's a big highlighter. Oh, that's going to work real well. That area is what I want. So I'm hoping you look at this and realize the area I have shaded so perfectly, as you can see, because this is very blunt tipped. Yeah, make that a little narrower. Is half of the distribution. So you actually didn't need any technology to do this. You're like, oh, well, if it's half the distribution, half the area is covered, the probability should be half. Hopefully that's not too tricky for you. Where this becomes a little bit more difficult is when it's not perfectly half or perfectly on a line. So there, we'll call that roughly my center. And then about 1 away in each direction is about here. So I only need the first one on there. And here I want the z's that are less than or equal to that. So again, less than or equal, we've always seen as to the left. We saw this in chapter 6 as well. Lefts tend to be less than or equal to, well, lefts are less than or equal to. So I'm hoping you're picturing, oh, I see how Minitab's going to factor in here. So if I want area to the left of 1, I know immediately from looking at this, it's got to be more than half, because half of the distribution is colored, and then I've got this extra. So let's figure out how much that's going to be. And to do this, we're going to use the table. So I'm going to pull up the table now. Here is the normal distribution table. So they used to give out when you became a math major books of these where there are pages upon pages upon pages of these types of tables. The Z table is actually one of the smallest ones, which is kind of fun, but to read it is very difficult. So here's where you're going to get into this. So looking along this first column, so reading down here, these are z-scores. So they're only through the first decimal place though. So you might ask yourself, well, how do I get the second decimal place? Well, that's going down the column. So basically your z's are on the margin here, and in the center are the probabilities to the area to the left. So that's very important. It's area to the left of the z-score. So for instance, my z-score in this question is 1. And so I want the stuff to the left of 1. So I want to look up the value 1. So I'm on the negative side of the z-score, so z-table, so I'm going to have to switch over to the positive side, which is on the back, essentially. It starts at 0, so I need to scroll down a little bit until I find the 1.0, and then I want the first column, because that's 1.00. So this would be equivalent to 1. So it looks like it's 0.84134. Point 84134. And just to make sure we're on the same page with this, let's look up one that's a little more complicated. So this time, here's my distributions are getting worse. There's 0, and then I want slightly bigger than 1. So if this is about where I'm putting 1, and I'd say this is probably about where 2 is, then 1.452 is probably like right here-ish. A little bit shy of halfway, right? So that's what I got to look up on the table. And the reason I know I have to look up that on the table is because I'm looking at less than or equal to. That means it's going to be the area to the left of that. I'm being sloppy with my coloring this time. So on the table, I'm going to look up 1.42. So I'm at 1. I need to go down to 1.4. And then I need to go over to 2. So 0, 1, 2. This is going to be the one I'm interested in. 9 and then a bunch of 2's and a 0. So did you follow that okay? 1.4 and then 2. So this essentially makes the last decimal place if you go 2 decimal places deep on these. So there's some rounding happening here that you should be aware of. Let's see, 0.92220. Alrighty, so then the next thing you gotta ask yourself is, what if I don't want to go right? Or sorry, what if I want to go right instead of left? That was awesome for an introduction. So here's 0. So it's got to be kind of close to 0. We'll call this negative 0.3. I made that bottom part crooked on purpose so it would fit. Yeah, and I want the stuff greater than or equal to it. So bigger. I want to go the other way. As we've already discussed, we know total area is 1, and this is the stuff to the right. If the table gives me the stuff to the left, how I'm actually going to do this is instead, I'm going to not do it. I'm going to do 1 minus the probability that z is less than or equal to negative 0.33, because negative 0.33 I can look up on the table. So this is going to be 1 minus, and now I need the table. So let's see, got to go back to this, and I need to scroll up to the negative side. So I want negative 0.3, so I'm in this row. And then remember, the first entry is 0. That's the thing you got to watch out for. So 0, 1, 2, 3. I'm writing this one down so I don't write the wrong one. So negative, be subtracting 0.37070, which will be 0.6293. Okay. Moving on up. Let's do another right. So with this one, I want to do greater than or equal to 1. Usually when I do these, I do reds as right and blues as lefts on the board to kind of keep them separated in your mind. I don't know how well this is going to work. So here's 0, and here's 1, and I want the stuff greater than or equal to 1. So I want this stuff. Alrighty, so I just need to do 1 minus whatever comes up on the table. Oops. So where's the table? There she goes. So I need 1, which is positive 1. Oh, we got that guy earlier. I could have just looked him up previously in my notes. That's okay. So I'll do 1 minus 0.84134, which we calculate real quick and get 15,866. You'll notice that some values come up a lot in this because, well, symmetry. Here we go. Moving on to F. F is the one that scares people for some reason. So here we are at 0, and it's like, oh, take a look at F, compare it to E. Is this the same one? I don't know. Notice that F is missing the equal to. So I know you get taught in finite math to do a dash line for this, so I'm going to do that real quick. But it actually doesn't matter, and that's what I'm going to get into right now. So remember, how we do probability is actually by area. And I talked to you about this in chapter 6 when we were looking at the binomial and the geometric. We had blocks because everything was discrete. So everything wasn't smooth like it is for this continuous graph or this continuous normal variable. And actually, if you think about the width of the boxes, since it was discrete and everything was counted as whole numbers, they all had width 1, and we did heights as probabilities, so width times height makes the area. Here, since we're doing area, does it matter if I have a line there? Do lines have area? They're actually infinitely thin, so it being there or not doesn't matter. Another way you can think about this is doing all the values bigger than 1, which there's an infinite list, yeah? So there's infinite number of numbers here. Whether or not I include one single value isn't going to have an effect on what happens. So not including 1 here doesn't change anything. It actually turns out to be the same. This is kind of like back in the day when you would argue with like your siblings. They're like, I hate you infinity minus 1 or infinity plus 1. Well, infinity plus 1 is actually just infinity again. Fun fact, you weren't actually winning by doing that. Darn. Feel free to try that one the next time you go home and see your family. I don't know. That should be fun. Alrighty. Let's do something a little more difficult. So if you notice, I did left, I did right, I did, hey, I don't need an equal to. So now I'm going to do an in-between. So you'll notice that as I go through this, I start dropping my equal to's like they're hot because I don't need them. And I'm lazy, so I'm not going to write all the numbers I don't need to. So I'm just drawing out what this looks like because I want to make sure my calculations make sense. And here's where we have a little bit of problem with the table. Now, when we do this with Minitab, you'll just select middle. So you won't care about the fact that, what we need to do with the table. Since the table only reads stuff to the left for area-wise, I have to be very careful how I do this. So essentially what we're going to do is I'm going to look up 1, which will give me what I'm drawing out in blue. Which you'll notice is too much area because it doesn't give me the yellow. It gives me the yellow and the white. So what I'm going to do is I'll calculate the stuff less. I am doing the wrong one. Yikes. Well, here's hoping I can edit this video, because this is completely wrong what I'm doing right now. Were you freaking out that whole time? Like, why is she doing 1 and not negative 1? I was trying to do the next one. 0, negative 1. There we go. I want the yellow. Jeez. So what I'm going to do is I'm going to look up 0, because that's this stuff, which is actually too much stuff is what I'm trying to say. So how do you get rid of something in math? Well, you subtract. So in blue, I'm going to have the stuff less than or equal to 0. And then what I'm going to do is I'm going to subtract off the stuff I don't need. So the stuff I don't need is the stuff right here in white, which I'm going to color in red to kind of emphasize it a little. So what's the stuff in red? Well, it's the stuff to the left of negative 1. So I'm just going to subtract off the probability that you are less than negative 1. And this should work rather well. So we've done the blue one already. It occurred earlier in our notes. That was 0.5. I haven't done negative 1 yet, so I'm going to have to look that one up. So I got to do the stuff to the left of negative 1. Let's pull up our table. And where are we at? Where's negative 1? Ah, right there. Oh, yeah. Yeah. There's another symmetric value coming up for you. And this makes sense to you. Stuff bigger than 1 should be the same as flipped over on the other side using symmetry to the stuff going less than negative 1. So that value came up again. 0.15866. So we're going to subtract those two real quick. So I'm pulling out my calculator. Typey. 0.34134. That's another value that we saw coming up earlier too. Woohoo! So let's do one more middle before we move on. because these two are just repeats and more practice, but, you know, good times. As always, I always am going to mark 0, and then I went between -1 and 1, so that's this area. So I want you to guess what I'm going to write next is the subtraction I need to do. So I want the probability z is less than something, and then I'm going to subtract off, oops, that was supposed to be a subtraction, something else to get the yellow area. So I'm always subtracting off the smaller area to get the in-between parts. So the smaller area is going to be the stuff less than -1, and this bigger area is going to be the stuff to the left of 1. And luckily we already have 1 up here. That's 0.84. 1, 3, 4. And the stuff left of -1 we have on here as well. That's right there. 0.15866. So let's do that subtraction real quick. Oops, I missed a decimal point. So that's 0.68. 268. I'm going to check and see what time I'm at this point. Make sure I'm recording. Oh yeah, that's awesome. Alright, cool. So that's how it works with the standard normal distribution. What I'm going to move on to doing next is, well, the not standard normal distribution, what you're more likely to see in the working world, other normal distributions, non-standard ones, but we'll see how this gets fixed real quick. So suppose on an exam where the scores are normally distributed with a mean of 80 and a standard deviation of 5, a student's exam is selected at random. Find the probability that a student scored below a 75, above a 90, between a 70 and a 90. So this is how this is going to work. I'm going to draw it real quick. I drew that too low. Let me undo that. Make it a little higher so it fits a little better. So I'm going to draw this one out. So again, normal shape, so bell shape, symmetric. Got to have that unimodality. My mean this time is not 0, it's 80. I'm going to mark off roughly where my standard deviations are, and I'm actually going to list what they are too. So 80 plus 5 will be 85, plus another 5 will be 90, plus another 5 will be 95. That doesn't quite fit very good, but hopefully your picture looks better than mine. Subtract off 5, so it's going to be 75, 70, and 65. Alright. So if we want the below 75 mark, we're right here. We want the stuff to the left of it because we want the values below. So I'm going to rewrite this as a probability statement. I want the probability that my score is less than or equal to 75. So 75 is not on that normal table, the z table, so I can't do this. But I can do it as a z, not an x. So what I want to do is I want to convert this into z's. So I'm going to change it into z-scores, and that I'm going to be able to do. So I'm going to take 75 and make it a z-score. And then I'm on the z distribution, not the x. So 75 minus 80 divided by 5. And that'll give me a -1. So z is less than or equal to -1. And we looked up the -1 a little bit ago, so I'm going to just roll up and grab him real quick. There he is, 0.15866. So only about 15%, well almost 16% of people scored below a 75 on this exam. That's pretty good. You know, your range of C's and below are pretty small for the class. So what I did here, you'll notice, is I took things that were on a standard normal distribution and turned them into, on a non-standard normal distribution and changed them into a normal distribution. What I'm essentially doing, and I'm going to go back to the first page, so don't get dizzy by me like rolling, is I took x's, something on a non-standard normal, and I changed them into z's by just using this formula. So this is incredibly important, that exchange between the two, by doing z-scores. As it turns out, anything you can go one direction in math, you can also go the other direction in math, so we'll do those second though. Let's finish up changing x's into z's. Come on. Oh, I scrolled too far. It's my bad. Alrighty. So same idea, only I want to do above 90. So I want the probability that my value is greater than 90, so I'm being lazy here and just writing a greater than instead of greater than or equal to. I'm going to use the graph above too and just shade it in like this. Oh yeah, that's super lazy. So I'm going to change this into z's. So I'm going to subtract my mean. Oh, not less than, I want greater than. Uh, 90 minus 80 over 5. That 90 looks like a 40. So when you do that, you want the probability that z is greater than -2. Remember that from what we've seen so far, to do a z as a greater than, you need to do 1 minus instead. So I'll do 1 minus z is less than -2. So I'm going to look up -2 on the table. That is not the right button. I'm on the negative page. This one. 0.02275. 0.97725. So that's pretty high. So the probability that you scored above a 90 is huge. That's wrong. Oh, I did -2. Ugh. 90 minus 80 is positive, teacher. I'm going the wrong way. Oh no, erasing this is not easy. Hold on a second. Sorry about that. My alarm was going off. I was afraid you guys were going to hear it. Anyway, so greater than 2. 1 minus, now I'm going to do less than or equal to 2. Or less than 2, same diff. I wonder where that phrase came from. I need 2, not -2. I was going the wrong way. It was way too big from our picture. That's the other reason I like the pictures. You can check yourself before you wreck yourself. Oh, there's the 0.97725. Good times. So let's see, I gotta do, if you're good at some algebra action, you already know what this is going to be. 0.977, not 2, 25. When you do that subtraction, that's when you'll get 0.202. 0.02275. Reading numbers out loud. It's a challenge. Alright, so here we see a middle. So I'm hoping you notice how this looks. Oh, look, I did a left. Oh, I did a right. Oh, I did a middle. You can do all the same stuff. So I'm going to do a quick sketch right here. And I'm also going to trick this into putting that on the right page because I don't know why it did that. Word. And if you notice looking at the information above, 70 is 2 in this direction. Woohoo! And 90 is 2 in this direction. So if I was to write this as a probability statement, I would say x is between 70 and 90. Note the direction of the arrows. Sorry, the inequalities. This is saying that when I look at 70, x is a value that is greater than it, and when I look at 90, x is a value that is less than it, so x lies between 70 and 90. If you point them to where they're not going the same direction, this is nonsense. Fun facts. So if I change this into z, woo! The z's got to be in between as well. We already did 90, we know it's a 2. P.S. by the fact that we know that this is 2 standard deviations below, 70 is a -2. So when I do this, I'm going to have to do the probability that z is less than 2 from the table, and z is less than -2 from the table. And the alarm is going off again. I don't know if you guys can hear this. I'm sorry, I must have hit the wrong button to get rid of it. So thankfully I have less than 2 up here. That's that 0.977. I keep wanting to put a 2 there. 5 minus, now I gotta look up -2 on the table. Where's -2? I already did this one, didn't I? I know I did. It's right there. 0.02275. If you're thinking I'm choosing a lot of the same values on purpose, It's the symmetry, man. It really makes it happen. That's supposed to be a 0. 2, 2. There's the two twos. 7, 5. And this should be 95 something. 0.945. If you want to know how I know it's close to 95, and how I knew that other one was going to be close to 68, you'll see in a minute. Promises, promises, man. Moving on. So you're hopefully looking at this and being like, oh yeah, 1, -1, that lies right on the values. That's kind of easy. Can I do other ones? Well, yes, you can. Let's look at curves. So suppose you're looking at a standard normal distribution model and you've got car fuel efficiency for the state of Michigan. This is from real data. I did round this value and the standard deviation to make it slightly easier to work with. Sorry. We know the mean is 24 and the standard deviation is 6. What percentage of cars get less than 15 miles per gallon? Which is not very good. Wonder how I picked 15. I don't remember. Oh, I think that's what my first car ever got. Or it wasn't a car, it was a truck. So there's 24. I know that 15 is less than the mean. So I'm just going to place it. Let's see, how many standard deviations down is that going to be roughly? So -6 will put us at 18. And -6 again will put us at 12. So it's got to be somewhere between 1 and 2 standard deviations away. So I'm going to put it like right here. There's roughly where 15 is. We want less than that, so we want it this way. So the probability, my value is less than 15 miles per hour. So I want to change that into a z. So I'm going to do 15 minus 24, because 24 is my mean, divided by my standard deviation of 6. Woohoo! So that's going to be the probability that my z is less than -1.5. This is kind of nice because all I got to look up is 1.5, -1.5, sorry, rather, on the table. So let's go get that done. So here we go, back to the table, -1.50, so it's that value, 0.06681. That's not very big. So slightly bigger than 6%. I wonder what percentage of cars get between 20 and 30. This is the pretty typical range of modern cars, by the way, is how I picked 20 and 30. So 20 should be pretty close to 24 because it's not quite 1 standard deviation below, and 30 should be exactly 1 above because it is exactly 1 standard deviation away from the mean. And we're doing this area right here. So this should be pretty close to like 60 is what I'm going to guess it's going to be. So I'm looking at between 20 and 30. So I got to change this into z's. So real quickly this time I'm just going to on the side do my subtraction and division. So this is -0.6 repeating, so I'm going to round this -0.67 because our z-scores table only goes to 1 standard deviation away, or sorry, bleh. Now I'm just saying crazy stuff. It only goes 2 decimal places deep. So even though I would like to do this in more detail, I can't using the tables. This is why they used to give out books of these, because you could then get more places if you had more pages than just one. Oh, this is just going to be 1. Why am I calculating this? Either way. So to do this, I'm going to do the probability that z is less than 1, since that's the z-score that goes with 30, the bigger value, minus the z-score for the lower value, -0.67. So I got to look up both of these. Well, I think I have 1 earlier, and I'm going to grab it anyway. We're on the negative page, so we'll go to this one. So 6, 0, that will be, so 0.60, 1, 2, 3, 4, 5, 6, 7. So 0.25143. And then real quickly, I'm going to grab the one for 1, since I'm on this page. Oh, I should have known that one. 0.84134. We see that one a lot. 1 is so common. Let's write those both in here. So I got 0.84134 minus 0.25143. So when you do that, equals 0.8, sorry, 0.58991. So that's pretty accurate with my, hey, I think it's going to be around 60%. It's not magic, I know the math behind this. You get to know it in like 2 examples, so calm down. Alright, more than 40, so I gotta do a right tail. So here's 24. Been doing right tails in red. 40 is definitely not placed where I'm putting it, because it's definitely further away, but here we go. More than 40 miles per gallon, so you probably have a Prius if that's the case. Woohoo! Prius! Let's change this to a Z. So you do 40 minus 24, and then you'll get 16 from that and divide that by 6, and you'll get, it's supposed to be a greater than symbol, my Z is really low, 2.66666666666, so change that to a 7 because I'm rounding. Ooh, I don't need that line on top because that's not true. I rounded it to 7. So that's what I'm going to have to look up on the table, but be careful, the table only gives you lefts. We're doing a greater than, which is a right, so I got to do 1 minus and then look it up on the table. So I'm going to have to subtract what I get from the table. Back to the table I go. I need some 2's and stuff. I'm going the wrong way. 2.6, 1, 2, 3, 4, 5, 6, 7. I counted that wrong. I did 1, 0, 1, 2, 3, 4, 5, 6, 7. I almost did that wrong. I almost made the common mistake. Can you tell I don't use the table that much? I'm a big fan of technology. I think it shows a little bit in this section. It probably does in every section. So 1 minus 0.996, man, to 1, which will give you a 0.00379. That's pretty tiny. That's super small. It's 0.3%. Well, 0.4-ish is closer. But still, not 4%, not 3%, 0.4 or 0.3%. Not good. So I'm hoping you notice how these go. I usually draw the picture because it helps me make sure I'm going the right direction and doing the right subtractions. So what I do is you start out by writing your probability statement with the x's, convert it over into z's. Make sure that z is something you can do on the table, aka looks left, not right, because you can't get right. And then you look it up on the table. So for instance, with this rights, like the red one, hey, I had a right for my x value in my probability statement. So what I had to do is, once I had it as z's, I did 1 minus the z value, look the z value up on the probability that goes with that z score up on the table, subtract it from 1 to get my correct value. So how do you do this? I have an x, I change it into a z. I maybe have to do some subtraction, maybe not. Get my probability, that's my answer. So what we're going to do now is we're going to go backwards, because that seems only natural. If I can go one way, I can definitely go the other. This is the natural dichotomy behind mathematics of, hey, I think, where was I going? Like, things have opposites. Like, I can add, I can subtract, I can multiply, I can divide, I can do roots, I can do exponents. Pretty much everything is undoable. Alright, so mean 24, standard deviation 6. We're still doing mile per hour of cars, only here I'm like, hey, find the cutoff value for the lower 20% of data. So the lower 20% of gas mileages. So I don't know the value, but I know the probability. Oh, I was supposed to do that in yellow. That looks horrible. And that was supposed to be a question mark. I love it when things look good. Neener, neener, neener. So I'm saying like, hey, I want the x's below some unknown cutoff value for where they start to be 20%. This is the same as saying on the z distribution, I want to know the z that's less than something. That gives me 20%. But the second part I can actually do. I can find a z-score whose area to the left is 20%. I go into the table, so if you remember the edges of the table are z's, the middle are probabilities. So I gotta find 20% in here. So I'm on the positive page, which is all bigger than 50%, because it's smallest it is up in that corner. So I'm gonna scroll backwards to the negative page. And what I'm looking for is something close to 20%. So how I usually do this when I was a student is I look down this first column and look for something that was close to 20%. So this is too small, 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 5%, 6%, too small, 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 small. Aha, right in here is where I'm close to 20%. So that's, whoa, whoops. Let's undo that. So somewhere in one of these two rows is where that 20%er is going to lie. So I'm just going to go down these two rows looking for it to get close. Oh, look right here. So this one's a little above, this one's a little below, and this one's like 0.003-ish away, and this one's 0.00045 away. So this is actually the closer one. So this is a value I'm going to use. So looking down here, the value that goes with this in Z is negative 0.801234. So I'm going to be using negative 0.84 as my Z. So I'm going backwards. I'm doing the table first instead of last. So my Z value, it is an unknown. No siree. It's, I should have used the eraser for that. Nope, pen. It's negative 0.84. Aha! Now, think back to what we did here. I know I got a probability. Bam. I got to a z-score. Aha. So now that I'm at the z-score, so I'm like here-ish. Got a z-score. Goes with it. I have to hop back to x. How do you do that? Well, you use the converter. So I know z. It's 0.84. I don't know x. I know the mean is 24. And the standard deviation is 6. So I just have to solve this. So you'll multiply by 6 and then add 24. I hope that algebra wasn't too fast for you, but it's not that complicated, so I hope it's okay. Negative 0.84. Where's my negative sign? Negative, negative. I'm hoping I'm not running out of memory. So 18.96 miles per hour. And I'm using my units here because this is an x value, so it has units. I'm going to pause this for a second because it's thinking. Sorry about that. Alright, what cutoff represents the third quartile? So hopefully you remember that the third quartile... Whoa. Nope. We might be having technical difficulties. Oh, come on. Okay, I'm going to stop for a second again and see if this will right itself.